So neutron stars are also pretty cool. If a star is too heavy to die as a white dwarf, then the next best thing is a neutron star. What happens is, remember that those electrons are snobbish and they don't want to get in each other's faces. Well, they look around and go, tasty little proton. I like him. So what happens is that the electrons, rather than getting in each other's faces, the electrons combine with the protons to form neutrons. So you get a ball of neutrons, all right? So in a supernova explosion, the outer part of the star explodes, and the inner part will collapse down to a neutron star, as long as it's not more than about 2 or 2.5 times the mass of the sun. And so you have a little ball of fast rotating neutrons, about twice the mass of the sun, only about 15 miles wide, incredibly dense. We're talking about billions of tons per tablespoon. Really, really, really dense. Denser than baklava, which I love, but which is really dense. Okay? All right. So how can you find a spinning ball of neutrons that's only 15 miles wide? Well, the answer is you can't find it unless it's doing something that brings attention to itself. And many, many neutron stars do exactly that. We discover them because of behavior that we call a pulsar. So here is my badly drawn, you're used to this by now, example of a neutron star. So stars rotate. Dead stars rotate as well. So this ball of neutrons is spinning. It's rotating around its north and south pole. Like the Earth, remember, our sun has a magnetic field. Stars have magnetic fields. And like the Earth, the rotational axis of this star is not exactly the same direction as the magnetic axis. So if you follow a compass on the Earth, it will not lead you to Santa Claus. Santa Claus lives at the north geographic or north rotational pole of the Earth. A compass leads you to the magnetic pole. Fortunately, on Earth, they're not that different. But let's imagine that there's a nice angle between the rotation pole and the magnetic pole. So as this thing is rotating, imagine the north magnetic pole coming and spinning around towards you and away from you. Okay? Now, there's one more thing we need here. The other thing we need is we need some free electrons or protons floating around on the surface of this ball of neutrons. Those charged particles interact with the magnetic field. So hopefully you've seen a picture with a magnetic field with these magnetic field lines looping around. When you have electrons or protons in a magnetic field, they'll get wrapped up in the magnetic field lines and they'll start going wee and whirling around. And as they do that, they will emit energy. They will emit electromagnetic waves, often radio waves. And those radio waves get channeled out the magnetic poles. Okay? Rapidly rotating, strong magnetic field, a few free electrons and protons, which will spin around, give off radio waves. The radio waves are channeled out the north and south magnetic pole. So what happens is as this thing spins around, you will see alternating pulses of radio waves. Radio wave, radio wave, radio wave, radio wave as it's spinning around. This is called the lighthouse model of a pulsar. I'll try to demonstrate this without killing myself, okay? So this is my rotational axis, and this is going to be my magnetic axis, okay? And so this would be my north magnetic pole, and this would be my south magnetic pole. And you're going to have to imagine that there's radio waves coming out. Why do I feel like I'm doing the chicken dance? All right, so here we have my north magnetic pole and my south magnetic pole. Every time one of my elbows goes in front of you, you're going to imagine that you're getting a pulse of radio waves. And so if you had a radio telescope, you would have no signal, pulse, no signal, pulse, no signal, pulse. And those pulses would be incredibly rapid and incredibly evenly spaced because of the fact that this thing is spinning like a clock.